Hello, and welcome to Network Wednesday here on Answer Everywhere. Today we're looking at the Linux code for sockets in linux/net/socket.c. This is a live show, an improvised live show, where every weekday, we jump into a code base that we haven't seen before, an unfamiliar code base, and try to find our way around. I've done a couple of these networking videos. The first one was on TCP, and then last week I did one on TCP dump. I think that a lot of people found the TCP video when they were looking for a different sort of content, maybe more like a college lecture or university lecture on how TCP works. And so I just wanted to say, as a sort of caveat, that that's not what this sort of video is about. It's not. This is not going to be me explaining how sockets work. This is going to be a video of a developer trying to understand a piece of source code that's important to the way that computers function, the way that the internet functions. And you can think of it as if you had to do some development, some programming, and you needed to look at the socket source file to see how it works. And you want to know things like what sorts of helper functions are there? What are the important structs? Do I really work with the low-level API, or is there a higher-level API that most people actually use? Those sorts of things, and also trying to get a sense of how the people who implemented this, what decisions did they make? What concerns did they have? All of those sorts of questions that you have to deal with when you're developing code. So that's the frame of mind that we're in. I chose sockets, socket.c basically for two reasons. One is it's gigantic and as a file, and two, that it's important to the whole Linux networking stack. So I think we opened the file in the TCP video, but it was really too large to take a look at. So I wanted to give it its own look. I don't have really any expectations about what we're going to find, or even that we'll find anything especially interesting. But we should at least walk away with a better sense of what's going on in the file, and if we needed to modify the Linux networking stack in some way, we'll be slightly better prepared after looking at this to do that. So that's the caveat. Now let's look at the code. I'm on the GitHub mirror. I think Linus probably has his own thing, and I think this is just a mirror. There's Linus. At any rate, I'm also downloading the code, so if we need to jump into a local copy, we can do that. All right, and so an implementation of the Socket Network Access Protocol. So the socket protocol, is that different from, I think this is the standard sockets. I think of it more as an API. It's possible I'm in the wrong place. We'll see what's going on. I see lots of Alan Cox, who we saw last time. In Linus, presumably that's the Linus. Arg, removed all the socket allocation altogether. It's in the inode now. Okay. It sounds like it's got the Linus personality shining through. Or is it someone will correct me if I'm pronouncing his name wrong. It might be Linus. I'm sure somebody knows and will tell me. All right. Okay, so this module is effectively the top-level interface to the BSD socket paradigm. Okay, yeah, that's what I was expecting. Cool. So this is BSD sockets. And I'm feeling like looking at my video that it might be lagging a little bit. So I'll check when I upload. Okay, so this module is effectively the top-level interface to the BSD socket paradigm. Cool. So we are going to hash include a bunch of stuff, as you might expect. But let's take a quick look at what some of the stuff is. We're going to include socket.h. which I don't have open, but I will find. And what else do we include? File, which is to be expected. Sockets are treated essentially like file descriptors. In fact, I think they might actually be the same as file descriptors under the hood. I think, so it's not surprising that we have file here. Net.h, I don't think we've looked at, but seems topically related to sockets, so that's not so surprising to see. Some stuff about interrupts, thread info, rc update, don't know what that is. Mutex, not surprising. If bridge is in if VLAN, these might be, if is presumably like a network interface, so this is networking stuff. I guess bridges and VLANs, sockets might need to know that they are bridges and or VLANs. Init, poll, they are the same, yeah. Press dot there. I don't know what that means, but hello? It will show up. Are you saying on GitHub to press period? I'm not sure what you're saying. Somebody's telling me in the chat to press there. I'm not sure if you're telling me to press dot. Dot seems to search for a literal dot for some reason. Okay. So what else do we have? We have high memory, mount, pseudo file system, security, syscalls, compatibility. KMod is probably maybe kernel modules, wireless, and some other stuff. Okay. And some IPv6 stuff, IPv6 route, and also regular route, which is presumably IPv4, and some like polling stuff. And we see kind of like right off the bat some things like socket close, socket poll, socket IO control, that sort of stuff. And since I'm done with the includes here, let me try to see if I can find the header file. And if we can, we'll look at that first. Now, I don't remember, maybe under include. So we have sock. But where is socket? Didn't we include socket? Socket.h. Is it in this directory? Is it in just not include? So first let's just double check that it's not here. And then let's maybe go to the root and then go back to net. And see if we have socket.h. No. Am I done here? Okay. See if we can find it here. Tip C. Include Linux socket.h. Okay. Let's try include /Linux. Let's try typing it in and see if that works. Cool. On a GitHub repo, press period. It opens VS Code and web. Oh, well, I'm not logged into GitHub. And I don't want to, thank you, Sabor. But I'm not going to, yeah, we're going to eventually get to a place where we are looking at tooling that understands the code better. But we're going to do that more gradually. And there are reasons, but right now we're just looking at the GitHub thing logged out. All right, so here's what I assume is the header. It's Linux socket.h, and we're going to import a small amount of stuff, including compiler. All right, and let's see how long it is. So 460 lines is pretty beefy for a header, I guess. We've got some structs, file, PID, cred is maybe credentials, socket and sock, and skbuff. And here is sock.h. which is part of the TCP/IP protocol stuff. We saw this comment basically in a bunch of other TCP files, essentially word for word, I think. And so how is sock different? It includes more stuff in the header, including a red-black tree, and C groups. So what does this mean? Sock seems more Linuxy. Maybe socket is more about the high-level interface to the BSD sockets API, and then sock is more like deeper into the Linux stack. So we've got this sock struct, and did we include sock? Not in the header, but maybe in the C file. No, just socket. Where did I find sock? Oh yeah, okay, we do include sock in the socket. So I'm going to take that as possible evidence that since socket.c depends on sock, it seems like sock.h is, and the corresponding C file for sock without the ET it's a lower level implementation thing. And then socket is the API. That's just a feeling I have. don't quote me on it, but we'll scroll quickly through sock. And it's long as a header, nearly 3,000 lines. There's something going on in sock. Do we have a sock.c? Let's see if we have sock.c. Here we've got net core sock.c. I think I was looking for sock before, so we'll open sock.c, and I think those will be basically the main files we look at, unless, we'll look at things as they come up if they're important to understanding the socket stuff. What was it? Net core sock.c. Hey, Linux net core sock.c, but I think Linux is just the name of the repo. Oh, it's because I have include here. Let's get rid of this include. All right, cool. So how big is sock.c? 4,000 lines. Okay, and then socket.c is what? I think less than that, right? All right, 3672. So similar. All right, let's do headers first and socket first. We'll just go in this order: socket.h, socket.c. No, we'll go in this order: socket.h, sock.h, and then we'll look at the corresponding implementation: socket.c and sock.c. Maybe, I don't know. I might get myself super confused. All right. So now we're in socket.h, which again, current theory is that this is mainly about exposing the Berkeley sockets API and is a little bit higher level than sock. So we get a socket struct, a sock address, which presumably SA is socket address. Is presumably socket address, and then SA family T would be, I guess, a family of socket address. And this is an address family AF XXX. So these AF things, let's see if we can find a whole list of them. Yeah, these are the address families. You can find this sort of stuff in the most descriptions I've seen so far of sockets include at least some of the popular address families. But when you create a socket, I think the first argument you pass in is like the domain, which takes one of these address family things. And unspecified is 0, which is a common pattern. But then Unix and local are the same thing, and they are like a connection to localhost. INET is the Internet IP protocol. There's some amateur radio stuff, Novell, Apple Talk. Then we get the multi-protocol bridge, ATM X.25, IP version 6, and a bunch of other stuff. DECnet, which I'm not sure what it is, security callback sudo AF. This must be using some security code. Anything else especially interesting? All RxRPC Bluetooth sockets. That might be interesting. Controller area network, InfiniBand, and Linux LLC. That sounds like a kind of business entity, but I don't. Maybe there's an LLC protocol. We have vSockets and a bunch of company-specific stuff like Qualcomm. Qualcomm. I think DEC. It might refer to the DEC company. XTP. Okay, so those are the address families. Here's a bunch more defines that are protocol families. And this is, I think, like the second argument. We'll look at the socket definition in a few minutes, seconds. I think these are defined relative to the address family. But the defines are just, I guess, defining it as, like, PF Unix is just defined to be AF Unix. So I guess that means AF Unix is 1. And so that means that this is also 1. All right, okay, so we've got Unix, local, net, mynet, and then many of the same things, I guess. All right, what other defines do we have? So flags that can be used with send and receive. All right, so these are flags that are used with send and receive. Things like peek, don't route, try hard. Synonym for don't route, okay. I don't know why try hard is a synonym for don't route, but there must be a good reason. Probe, trunk, I'm guessing truncate, don't wait for non-blocking IO, and a record, fin, sin, confirm, and error queue, fetch message from the error queue, okay. And more flags like zero copy, fast open, and then set sock options to level. Thanks to BSD, these must match IP proto underscore whatever XXX. So socket options, and we have things like TCP, IP, TCP, UDP, IPv6, and ICMP, and a bunch of other protocol stuff. This is raw is for opening, I guess, a raw socket. Packet, ATM, okay. So those should be most of the defines, and in fact they are. So let's look at things like structs and functions that are declared in this header file. So we have this check size thing, which is going to be like a compile time thingamajiggy that gets the size of some struct and calls it build bug on, which is maybe going to do some conditional behavior depending on whether. Now, I think we maybe looked at bug on before, and it was not like debug stuff. It was more like generate a bug if something bad happens, I think. Okay. So we've got socket address family types, and the socket address struct has a socket address family, which is the AF stuff that we looked at. And it's also got a union over socket address data minimum of 14 bytes of protocol address, or declare flex array car SA data. And it sounds like where's SA data defined? So it sounds like it has some sort of array, and maybe this is the buffer that you're going to put stuff in for the socket. And I guess this is so that the min might be because we want to make sure it has some minimum, a way of enforcing a minimum on the buffer size or something. All right, linger is whether to linger and how long. That I'm not sure exactly when linger is used. We also have socket address storage. And then message header. As we do 4.4 BSD message passing, we need to use a 4.4 BSD message passing system, not 4.3. Thus, message ACK writes of length are now missing. They belong in an obscure libc emulation or the bin. I'm guessing by bin it means trash can. All right, so message header is a struct, and what do we got? We've got a message name, a length, an inc, which is output data left in the socket, and is an int. And we have IOV iter message iter, which sounds like an iterator. Ancillary data. Message control user is the user buffer used for the receive side when message control user is set. Message control is the kernel buffer used in all other cases. So you've got this buffer, which is either user controlled or not user controlled, depending on what, on whether message control user is set. And we have the Boolean for message control is user, and we return INQ after receive. This is the INQ. I'm not sure what that abbreviation stands for. Probably not inquiry or inquisition. Inquest, or maybe it's just in, as in not out, and then Q as in a Q-U-E. Wait, how do you spell Q? You know, Q. That, Q-U-E-U-E. I don't know. So I'm not sure. I mean, maybe we could look it up. Message in Q Linux. I'm not sure this is super fundamental to know, but oops, what have I done? Inquire? Maybe it is inquire. Maybe it is inquire. Okay. At any rate, it's some out parameter, right, that's going to do what? I guess if you have data left in the socket, it's going to be here, but it's an int. So maybe it's just the amount of data left in socket. All right. Is there anything surprising here? I don't think really. And then we have this. Okay, so we've got a message buffer that I don't think we saw. And message IOCB, pointer to the IOCB for async request. CB maybe callback, input output callback. And we've got a message control length, which is just, I guess, an ancillary data buffer length, right? And then we've got this thing, SG from iter, of this is like a sock as opposed to a socket. So whatever this thing is in this file. An SK buffer, which is a socket buffer, I believe, and an IOV iter in the length. IOV iter we saw just a second ago. IOV iter. So why IOV? Input output vector? Maybe an iterator on the input output vector, since we have IOVec elsewhere. All right, and then we have a user message header, which is different from a message header. And maybe this is the user visible version or something. And we've got a message name, message length, message IOVec, message IOV length, message control, control length, and message flags. And for receive message and send message, we have this message header struct, which is also, MSG header. Oh, MSG header. So double M, which has a user message header and a message length. And just for completeness, let's look up, let me look up the main user-facing stuff. So here are the AI. So I'm just pulling up on a web page as opposed to on my machine the man page for, I think, socket 2 is where I am. Socket 2 here. And here's the AF stuff that we saw the defines for. Here is the socket type. And some more stuff. But what I want to know is, okay, so here's the main socket, I guess, entry point. It's going to take a domain, which is the AF thing. It's going to take a type and a protocol. Yeah. And what else do we have? Let's see if the Wikipedia page on BSD sockets. Somewhere I've seen, okay. So here's an example of API functionality. We've got socket, bind, listen, connect, accept, send, receive, send to, receive from, close, get host by name, get address info, select, poll, get socket opt, set socket opt. All right. So I just wanted to see if any of these structs we were looking at are like user facing, and they don't seem to be. These seem to be like implementation details. We've got a C message header, which has things like, I don't know what C is. Ancillary data object, information. Ancillary data consists of a sequence of pairs, C message header, and C message data. And they have things like the byte count, including the header, the originating protocol, and protocol specific type. All right, here's more ancillary data. Information macros. So these are macros, I guess you can call on things like space, length, user data, align, define. For each C message header is like an inline for loop thingy, I guess. Get the next message header. Please, in all caps, do not touch this function. If you think that it is incorrect, grep kernel sources and think about consequences before trying to improve it. Now it always returns valid, not truncating ancillary object header, but caller still must check that C message length is inside range given by message control length before using ancillary object data. Signed A and K. Okay. I don't know what this is. Is this supposed to be like an ISO type date? Maybe 98 is the year, but we don't have like a full four-digit year. I'm guessing this is from 98. Is that reasonable? And who is A and K? It's not Alan Cox, because his name is C. No. All right. So this function has a warning. Where did it go? Yeah, I kind of like stern warnings in code because they flag that you should pay attention to a thing, and if it's a warning, then that kind of implies that it's a common mistake to not pay attention to it, or to so that's useful as a pointer of like where to focus your attention. All right, so this is this function that has the C message next header that you shouldn't touch. If you don't know what you're doing, then leave it alone and assume that you are, if it seems wrong to you, you might be right, but check the kernel sources, and chances are that probably it's your understanding that's wrong, is how I'm glossing this particular comment. And we've got some more C message next header stuff. Given the amount of C message header like defines and whatnot, I'm going to infer that under the hood, a lot of the manipulation of networking data is going to be done in these C message structs and functions. And we've got a function data left that's just going to look at the IOV iter count on message to message iter. Data left, the iter count. So I guess my initial thought is that iter count would return something like, what is the value of the iterator? Like how much have we iterated? But it's going to return how much data we have left. So maybe it's something like the size of the buffer minus like where we are in the iterator. Let's see if we can find IOV iter count. No? Or I need R or something. It has its own file. Did I successfully grab that? No? Oh my. Whoop. Oh, this is what I wanted to head. Whoop. There we go. Okay, so let's grab this with Emacs just to open it quickly. Maybe the header. Did I spell that right? Let's try this again. All right. So I see lots of calls to IOV iter count. Bunch of butterfs, ceph, fuse, orangefs, sifs. Very interesting. Okay. Up here is the C file, but it doesn't seem to ever define IOV iter count. Okay, well, maybe it's like a define somewhere, and for some reason I'm not picking it up. Okay, well, wherever it is, it does something with the IOV iterators. Okay, so here's socket level control message types. Rights, access rights, credentials, security. Okay, and ucred, which has a PID, a UID, and a GID. And are those credentials? I guess it's, I mean, these are related to permissions. They help you resolve permissions for sure. I'm not sure what it means to call them creds, or creds might not mean credentials. Okay, so, and then we looked at a bunch of these defines already. And then we have these underscore extern stuff, like sys receive message, and I'm going to guess that underscore sys is a little bit like implementation. So this is maybe the implementation of receive message, send message. And the function signature looks like the socket function signature in man socket 2. Does it? Well, we take a file descriptor, a user message header, unsigned in flags, and forbid message, C message compat. So let's look up the receive message. I don't know if this is something I can ask for the man page for. No. Without the underscore, and we'll add socket and see what comes up. Receive message 2. Okay, so receive message takes a sock ID. Oh, okay, so the so this message header struct is user visible. All right, and it takes flags, and it returns an S size type. All right, and receive from is similar, but it takes a buff, a length, presumably for the buff, some flags, a socket address, and a socket length type, but no message header. And receive takes a buff and a length and some flags. The receive from and receive message calls are used to receive messages from a socket and may be used to receive data on a socket whether or not it is connection oriented. All right, it is normally used only on a connected socket and is identical to receive from, receive is normally, and is identical to receive from with a null source address argument. All three routines return the length of the message on successful completion. If a message is too long to fit in the supplied buffer, excess bytes may be discarded depending on the type of socket the message is received from. So this buffer, presumably this buffer, is an out parameter, is I guess what it's saying. So you're going to get your buffer filled up with stuff, and then you're going to get a size t that is presumably the amount of stuff in the buffer. Return the length of the message on successful completion. Okay. And what else? Yeah, that's receive. I think receive, at least I think send doesn't, like send like kicks off, it like adds something to a queue, I think, rather than actually sending, and then sending happens in the background. So let's look at send while we're here. Send message is also going to take a socket file descriptor, a message header, and some flags. And send is going to take a buffer, which is presumably an in parameter this time, and we've got a const to let you know that the function's not going to modify the buffer, and the length, and some flags. The system calls send, send-to, and send message are used to transmit a message to another socket. The send call may be used only when the socket is in a connected state so that the intended recipient is known. So this is for things like TCP as opposed to like just sending datagrams into the wild. The only difference between send and write is the presence of flags. With a zero flags argument, send is equivalent to write. And write, I believe, is the write to a file function, write to a file descriptor. So write is this function that you can call on like local files, like if I have some PDF or whatever, text file or whatever. Write is the function that you would call to write to the file, and you can also call it to write to a socket, which you can think of as kind of like a remote file, modulo some implementation details, but send also has these flags, and aside from the flags, it's the same as calling write. All right, so Nextnerf is suggesting I look at include Linux UIOH on line 268. I think this is a message from a few minutes ago, so I'll have to remember what the context was. Okay, so include Linux. Oh, maybe is this the definition of the thing I was looking for? Include blah, blah, blah. This should not be a dot. This should be a slash. Line 268. Dupe iter. We've got an IOV iter. Am I in the right place? Include Linux uio.h. Yeah, okay, so this I have the dupe iter. What was I looking for? IOV iter count. Let's see if that's here. Oh, okay, yeah, I see. 270, at least on my, on the commit I'm looking at. So IOV iter count is going to return just I count on the IOV iter struct, or yeah, thingy. So it is going to return the count. I don't know why that's the message left. Maybe it counts. Maybe it fills the buffer backwards, or it counts backwards. I don't know. Okay. So that's socket.h. Let's look at sock.h. And again, what I'm expecting is that, so I have this theory that sock.h is more about low-level implementation details. So I'm just looking to see whether that theory seems reasonable. I'll try to falsify it. I'll try to confirm it. But I don't think I'm going to look too much at the nitty-gritty details. And then we'll look at .c, socket.c and sock.c. And then if any details really jump out at us, we can come back to the headers as well. All right, so here's sock. Again, we have some sort of tree, a red black tree, presumably. Here's a good comment. This structure really needs to be cleaned up. Most of it is for TCP and not used by any part of the other protocols. And I think we saw at the beginning, it had the TCP implementation header, not header, statement. So this is telling me that like, well, socket is used for everything, right? So you do UDP on sockets, send datagrams. It has a bunch of protocols. Like we saw some InfiniBand stuff and some what seemed to be like custom proprietary protocols, but we also had, I think, TCP and UDP, right? Or did we just call that connection and SOL TCP and SOL UDP are two of these things. So it seems like sock.h, we are firmly in TCP land, or at least if there's non-TCP stuff, that's not the main character of this file. Okay. All right, so what do we have? You've got sock debug and a struct. We've got this struct, and this struct has a comment. It says, this is the per socket lock. The spinlock provides a synchronization between user contexts and software interrupt processing, whereas the mini semaphore synchronizes multiple users amongst themselves. Okay, and we have a spinlock, int owned, presumably not a Boolean, maybe an ID of the owner. Maybe it is just a Boolean. Wait queue head type. Okay, so some wait queue. And this comment says, we express the mutex alike socket lock semantics to the lock validator by explicitly managing the slock, presumably spinlock, as a lock variant in addition to the slock itself. And so if we have this thing set, we have a struct lock dep map, dep being what? Dependency map? Some sort of, I presume that the comment is about this. So something about validation. All right, so let's look at this again. It's a per socket lock, so every socket has a lock. And what does the lock do? It's providing synchronization between user contexts and software interrupt processing. So I'm guessing it means like transitioning into and out of like kernel context. You know, I guess whether things are running as like root or the user or something along those lines. Whereas the mini semaphore synchronizes multiple users amongst themselves. So when we're in like user space, it sounds like the mini semaphore is the thing that's keeping me from like monkeying around with my coworkers stuff. And then the spinlock is the stuff that keeps either of us from monkeying around with things that are owned by the kernel. That's my guess. But again, this is unfamiliar code base. I'm just trying to figure out what's going on so that, you know, I wouldn't testify to that in court. So we've got struct sock proto-net. They seem reasonable enough. This huge comment. Struct sock comment, minimal network layer representation of sockets. I think it had like SKC data, a foreign IPv4 address, bound local IPv4 address, a placeholder for inet deport, whatever this is, SKC transaction queue mapping, or RX, receive, RX I think is receiving, and then TX is transmitting, so the RX queue for the number, the RX queue number for this connection, the TX queue number for this connection. Wow, okay. So are these all used? Let's just grab one of these that looks hard to accidentally typo. SKC cookie, let's find it. Yeah, okay, so this appears in the struct. So this struct, these are like fields of the struct. And it's a lot of fields. And what is the benefit of doing all of these fields in one place? I'm guessing we're gonna see a bunch of unions, or maybe a giant union. And unsurprisingly, we start off with a union. Let's see how large this union is. Oh, we get many unions, yeah? Okay, 1, 2, 3, 4, 5, 6, 7, 8-ish. On the order of 10, let's say. Okay, so what is the first thing? The first field, I guess unions don't have like a field name, right? But the first fieldy thing is either an SKC address pair or a datter or a receive S adder. or rather it's either it's either an SKC address pair or it's this struct that has a datter and an adder, or datter and a satter. And the datter is a foreign IPv4 address, and a receive satter is a bound local IPv4 address. So maybe these are just send and receive. I don't know why DADR, destination. I don't know what the D is for. And then what else? We've got SKC hash or U16 hashes. And this is like a port thing. Either it's a port pair or it's this struct of a dport and a num, SKC num. So let's look at what dport is. Dport is a placeholder for the internet dport or TW dport. TW, I'm not sure. And SKC num is a placeholder for inet num or TW num. I don't know what num is in that context, but ports. It's some kind of port. And if it's not this kind of port, it's this other kind. We've got an SKC family, estate, reuse, which is an unsigned car, reuse port, IPv6 only. These these are named in a way that I would expect them to be booleans, but they're unsigned cars. So I'll look at a few of these. We have Nextnerf this union. So Nextnerf says this unions for sock common are used to access the same data into right. Yeah. So Nextnerf is pointing out, used to access the same data in two different ways. Oh, okay. So if I understand correctly, what Nextnerf is saying is that I mostly think of union types as a way to have a struct where either one thing or the other is populated, and kind of reusing the struct in multiple ways. The way you would have a union type in like type theory or like a functional programming language. But I think what Nextnerf is pointing out is that in a language like C, when you have the union type, there's like a fact about the world that when you populate something, there's like data laid out in the memory, and nothing prevents you from like writing that data, I think, as one of the union types, like an address pair, and then reading it as a different type. Is that what you're saying? And then that lets you essentially do these like automatic conversions between these two things. So I think that might be what you mean by accessing the same data in two different ways. I think I've seen that pattern. So they say, for example, SKC adder pair as one or a datter and receive are each for their own. I'm not sure I understand that, let's see, as one or as each for their own. I'm not sure if I understand that that statement, but let me know if I'm correctly saying what you're saying, that like one of the reasons this is here is you might need an SKC hash in one context, and you might need this thing in another context, and they're the same memory, so we can look at them in two different ways. Okay, so all right, yeah, all right, cool. That's what they mean. Great, thank you. That's useful. That's useful, and that's an interesting trick, I guess. As long as you're sure that the bit by bit representation that you have for one type is like what you need for the other type as well. Presumably some thought goes into cooking things up that way, but I think back in the day when all of this stuff was defined, computing resources were so constrained that was like a really natural, a natural thing to do and put thought into. Okay, so unsigned short. Yeah, okay, so let's look at these unsigned characters. Let's look at SKC reuse. SKC, so SR reuse adder setting. So this is a socket option. Okay, so let's look at why. I'm just curious why this is a car, what was it, an unsigned car? Is that just thinking of it as a field of bytes? Yeah, I think so reuse adder is like a flag thing, right? Define, yeah, so it's just like OX 0004. Okay, so basically thinking of it as a byte flag, I guess, is what unsigned car really means in this context. Okay, all right, HList node, this union of HList node, SKC proto, maybe protocol, and possible net T, SKC net. Okay, if we have IPv6 configured, then we also have two IN6 addresses. One is the datter and one is the receive satter. And I think that this is, again, the same thing that we saw up at the top. And this is like the destination address. And this is like where we're going to receive the replies. Maybe, presumably. That's a guess. All right, so the following fields are padded to, okay, so something about padding, let's look at it. Following fields are padded to force offset of struct sock sk ref count equals 128 on 64-bit arches, assuming IPv6 is enabled. We use this padding differently for different kinds of sockets. Okay, so we've got unsigned long SKC flags, SKC listener, timewait death row. Okay, SKC TWDR. All right, so, okay, so I didn't know what TW was. Almost certainly timewait, now that we see it expanded in this comment. Okay, and then we have some fields between don't copy, begin, don't copy, end, or not copied, and sock copy. Okay, so we can tell it not to copy some stuff. And yeah. All right, what else? Oh, incoming CPU. I guess that's needed for if you have multiple CPUs. And it will tell you where to look for the stuff you're looking for. Then we have an SKC receive WND, presumably receive window, and TW receive next, TCP timewait sock. So I don't know what timewait is. We'll look it up in a second, but just for the, I like to, you know, make a guess before I look something up, just so I have something at stake. I feel like it helps you learn a little bit. Okay, so presumably timewait is going to do something like, you know, wait, wait on a clock, I guess, before I check something, receive next. So maybe this is going to tell us, you know, instead of like, you know, maybe there are different ways of polling. So let's look if we can find this just as a string on the internet. Here we go. This is the reference, but all right. It's in tcp.h. What if we just look up timewait? How to fix the timewait, how to resolve timewait, exploring timewait status. What is timewait state? Timewait is a state in the TCP connection process. A socket will be in the timewait state after it has received a FIN from the remote side. Oh, okay, so I was wrong. After that point, the socket will automatically close itself. This ensures that old connections are properly shut down and prevents any errors or data corruption during network communication. And as part of the, we get an RFC, TCP protocol connection close, as described in the transmission control protocol, section 3.6, closing a connection. All right, here we are. Let's see if we can find timewait. Time dash wait. Return state equals timewait. Timewait state segments are processed in sequence. I think I want the first one, or maybe I just want to go back to whatever this entry point is and look for the right string. Here's fin wait, and here's time wait. When a connection is closed actively, it must linger in the time wait state for a time of 2x MSL, maximum segment lifetime. However, it must accept a new SYN from the remote TCP endpoint to reopen the connection directly from time wait state if it does some stuff. Okay, so time wait, when you're asked to close, we've got this maximum segment lifetime. And time wait says we have to wait for twice this lifetime. And if we receive some stuff during that time, we might have to reopen. And presumably 2x is to allow for something like a round trip, like a worst case scenario sort of thing. That's the sense I have. I'll leave it there. We have some BPF local storage and an SK filter, like a socket filter, which I don't remember if we looked at that last time. Here's another giant struct. Is this the same struct? This is a different struct, right? Okay, so this is some struct sock network layer representation of sockets. The network layer representation of sockets, okay? Shared layout with inet time wait sock. We've got shutdown user locks, more locks, kern sock, true if the socket is using a kernel lock class, a receive buffer, a wait queue, some destination and receive stuff, a flow policy. All right, this is getting interesting. Whether we need to confirm, pending confirm, a write queue, a wmem queue, which is a persistent queue size, wmem queued. Okay. Reserved memory, allocation something or other, the allocation mode, pacing rate, if supported by the transport or packet scheduler. Now we're really getting into, no, I don't know how to describe it, but like we're getting into things like memory allocation, scheduling, some of the more low-level queues, and this seems to be where the real work, I guess, is done. Some call and a bunch of locks and a callback lock, error, peer PID, peer credentials, peer lock, which is the lock protecting the SK peer ID and SK peer creds, protocol, which protocol this socket belongs in this network family, and what else? Timer, the sock cleanup timer, timestamp of the last packet received. An SK socket, write pending, a write to stream socket waits to start, state change, data ready, reuse port CB, reuse port group container. Is CB callback? I don't know what group container is in this context, or what CB means. All right, destruct, called at sock freeing time. Sock freeing time. It sounds like maybe you're like getting home from work and taking off your socks. I'm gonna start calling that sock freeing time. Okay, so validate, transmit SKB. All right, so we are in lower level land for sure. And this is the sock header. So I'm going to say that my theory that sock is the lower level implementation details has more or less been confirmed. At least in my mind. you might remain skeptical. Okay, so and we're going to define a bunch of stuff, and all of this stuff is defined as this __ sk comment stuff. What seems to be going on in the kernel is that the __ stuff is like implementation. So I'm going to assume that's more or less what's going on. So this is saying that like sk prot, which I nearly read as sk port, is implemented by this. This is the real function, and this skprot here thing is just you know, a higher level view on this lower level function. Early demux fields. So I guess early. I don't know if in C. I guess things that are earlier are maybe are they faster to read if you have an index? I don't know. I mean, maybe if they compute the index, then it's faster to read. But at any rate, these are early, at least in the sense that they are, at least in the sense that they appear sooner in the struct. They might also be earlier in the sense that they are, that we're like switching on these fields more often. And they have things like the SK, Rx, I guess, like receive destination, receive if index, and destination if index, and the destination cookie. So that seems like demux, meaning I guess we're going to get a bunch of stuff and we're going to demultiplex it. So I don't know what the bunch of stuff is, but you might imagine that, you know, somehow you've got packets going into your network card, and maybe they all go into the same queue, maybe on older cards. That's what they did, and maybe newer cards do something fancier, but let's assume for now they all go into the same kind of like queue sort of thing, and then the operating system looks at that queue and like delivers them in the appropriate places, like delivers, you know, if something's going to port 43, it delivers it to port 43. And you might consider that a type of demultiplexing. Is that the demultiplexing we're doing here? I'm not positive, but it's maybe that sort of flavor. We've got a socket lock drops. Maybe it's an atomic type, atomic T. Maybe this is some sort of count of drops. Let's look up SK drops. All right, 2 of 5 matches. Okay, raw UDP drops counter. So it's a count of, I guess, UDP packets or datagrams that have been dropped. Your mic gain is too high. Oh, okay. Am I clipping? Thanks, Wrath. I might be talking louder than I usually do. Let me try moving the mic away, and let me know if this fixes it. Racksniff says it can be better to put stuff at the start for performance in C2 because it avoids cache misses. Yeah, that's the other thing I was wondering, but I couldn't think of a reason why it would be better for cache message for cache performance. Maybe it has something to do with, like, if these are these are earlier and you're loading stuff. I don't know. Maybe just the stuff at the end gets just loaded into the cache less frequently, or it goes away faster for some reason. Yes, I'm clipping a little bit. Okay, yeah, I can lower the gain. Why don't I start by lowering the threshold on the limiter? So that should lower the max. And Wrath, please let me know if this fixes it. If not, I can lower the gain elsewhere on the chain. I'm reluctant to play with the gain staging too much live because for reasons. But that is useful feedback. Thanks, man, or thanks, human. Okay, so all right, where were we? Yeah, okay, so Rackstep was saying that, like, it could help cache performance to put stuff at the start, which is not surprising. I'm not sure. Let's look it up. Cache performance struct order. All right, so does accessing a single struct member pull the entire struct into the cache? The hardware does not know at all about the struct, but it is true that the hardware load in the cache some bytes around the bytes you are actually accessing. This is because the cache line has a size. It does not work on a byte by byte access, but on, for example, 16 bytes sizes at a time. You have to be careful when ordering the members of the struct so that often used members are close to each other. All right, so, okay. A little bit better, just a bit of rattle left. Yeah. All right, thanks. A little bit better. I can try, I'll try backing off the gain. Maybe down here. And that this looks basically the same on my level, but maybe put this back where it was and then change it on the compressor. Is that any better? We'll try that. I think this is a thing that I probably can't really fix until I'm offline and take a look at it, which I definitely will do. I don't want to break anything right now. Okay, so what I'm seeing is that the thing that really matters is, where did it go? That your things are close together. So that often used members are close to each other. Sounds better. Okay, great. Thank you. Thanks for letting me know. And anyone, I had a sound issue on one of my videos, and it turned out that the reason was that I recorded mono, but somehow the left and right channel of stereo were out of phase, and so like I really like to get feedback like this because I want my sound to be good. I want my quality to be good. I'm somewhat limited in the hardware right now, but there's always like lots of settings I can tweak. And sometimes you tweak a setting and then the total performance tanks for some reason. So it's a little bit, in my experience, at least on Linux with my particular graphics card and sound card, it seems like things are a little bit fragile. So I'm a little bit reluctant to change too much at once, but I really do appreciate this sort of feedback. Okay. So, all right. So we want things that are used frequently to be close together because they'll be loaded into the cache at the same time. And presumably there's some sort of alignment issue, right? So it says 16 bytes at a time. You can presumably do things like change the order of the struct and test whether cache performance is better or worse on that particular processor. And so in the interest of having things grouped together and like aligned well, presumably, that's probably why these three fields are at the beginning. Because they're, you know, if this whole thing is aligned at 0, I guess the fields are aligned at 0, and so they're easy to grab. Some obtuse FFmpeg incantation. Yeah, that's exactly right. That was basically my experience for the first several weeks of streaming, is spending like 4 hours at a time trying to debug audio and video issues. It turns out I should have just bought an NVIDIA graphics card. I bought an AMD one during the graphics card shortage, and you know, apparently the NVIDIA had like a proprietary encoder is like the thing that everything should be using on streaming. So in practice, even though I have a relatively nice like graphics card or whatever, everything is actually encoded by the CPU, and just stuff like that. Okay, all right. So yeah, where are we? All right, SK write Q peek off. So these are all just, you know, structs that we saw when we were glancing through. We don't see as many unions, I don't think. We see a few unions, write Q stuff. But this struct seems to be like everything the kernel needs to make this, make networking decisions. And it's all just kind of packed in one place. And presumably it is grouped for cache performance. Like maybe if we blame on the struct, we might see some optimization commits, pull requests, whatever they call it in the Linux world. We want blame. This might make GitHub ground to a halt. Yeah, I've got a black screen now. All right, well, okay. Let's find, where was it? There's some like write queue stuff, maybe. All right. Let's see. Reorder struct sock fields. That looks promising from 13 years ago. Fix all kernel doc warnings. That's maybe less promising. Reduce structures when xfrm is equal to n from 15 years ago. Okay, so that commit added this if-def here, possibly among other things, and that reduced the structures, so you have less structure size. So that seems to be an optimization. Reorganize struct sock for better locality. Whoever this guy is with the mustache and the hat, Dave M330, David Miller, seems to be on top of optimizing the structure order for performance. All right, so here's which commit came for us. Let's look at the first one first. Do we have a date? November 16, 2010. And then here, I think it's the same person, right? Wait, this is Eric. Yeah, okay. Eric Dumazet. Oh, and Dave, I don't know which one is which. Maybe it's this guy. Well, this is Dave MM, but it was authored by Eric Dumazet and committed by Dave. Okay. So is this also Eric? I'm going to credit the right person. Seems like Eric is writing these commits and not Dave. And Eric is at Google. Okay, all right, cool. So maybe unsurprisingly, Google is committing or submitting patches to improve cache coherency or cache performance of these structs. But let's see what the commit message says. So right now, fields in struct sock are not optimally ordered because each path in parentheses rx soft IRQ, tx completion, rx user, etc. has to touch fields that are contained in many different cache lines. The really critical thing is to shrink number of cache lines that are used at rx soft or IRQ time. CPU handling soft IRQs for a device can receive many frames per second for many sockets. If load is too big, we can drop frames at NIC level. RPS or multi-queue cards can help, but better reduce latency if possible. The patch starts with UDP protocol, then additional patches will try to reduce latency of other ones as well. Interesting, so we're starting at UDP. Why UDP? I think, what year is this? We had a year, right? 2010, let's look up QUIC. Is QUIC based on UDP? So QUIC is a general-purpose transport layer network protocol initially designed by Jim Roskin at Google, implemented and deployed in 2012. So this commit is before QUIC was deployed. It was initially an acronym for Quick UDP Internet Connections. Yeah. Let's see. It's based on UDP. Okay. So I think if I remember what's going on, essentially QUIC is an implementation of something TCP-like, but based on UDP. Okay, so QUIC aims to be nearly equivalent to a TCP connection, but with a much reduced latency. Yeah, so Google was doing lots of UDP stuff, and maybe like 2 years before QUIC happened, maybe they were working on it for a few years. One of the Google employees comes in saying we need better cache performance on UDP, and yeah, so they're going to reorder stuff. And I'm not going to look at the details because for this purpose, details are not as important. It's just I want to understand, cache coherency is an issue in how you order the struct, and if you want to, and things should be close together and stuff like that. Okay, so group. Here's another commit by the same author, but I think a few years later, 2016. Group fields used in txpath and keep some cache lines mostly read or read to permit sharing among CPUs. Mostly read. Does this mean as opposed to like read write? Group field using the transmission path and keep cache lines mostly read. So if they're mostly read only or read mostly or whatever, then you can share them among CPUs. And we're going to optimize this struct so that things that are read together presumably are close to each other, and that maybe keeps them in the cache. If I remember correctly, each CPU gets its own cache, then there's like a cache shared among the CPUs. All right, we're going to look up CPU cache architecture, structure. Let's just look up an image. What is CPU cache? Let's look up maybe Wikipedia. A hardware cache by the Central Processing Unit. Overview. All right, so there's an instruction cache, a data cache used to speed up data fetch and store, and a translation look-aside buffer. But what I want to know is how many caches there are. Let's just ask if there's a per CPU cache. Yes, it varies by the exact chip model, but the most common design is for each CPU core to have its own private, that's what I was looking for, L1, its own private L1 data and instruction caches. On old and or low power CPUs, the next level of cache is typically an L2 unified cache. It's typically shared between all cores. Wait, old and low power? Does that mean we no longer have L2 cache? Or does it mean that L2 is different? Yeah, L1, L2, L3 cache. It's often more capacious, which is just a fancy word for bigger. I don't know why you need to use a word like capacious in this context. Okay, so here's a diagram. So the CPU core 1 has an L1 cache for instructions and an L1 cache for data, and similarly CPU 2. And it looks like, in addition, each CPU now has its own level 2 cache, L2 cache. And then we have an L3 shared cache. Okay. But now I need to know why I'm going to guess that L2 is just bigger and maybe a little bit farther away, and so slightly slower. But at least in that diagram, still seems to be per CPU. And then I think the first thing we saw is that L2 used to be separate, but now L3 seems to be the thing that's shared among CPUs. And at any rate, cache lines that are mostly read to permit sharing among CPUs, that's going to go in, I guess, L3 in that diagram. And it's going to kind of stay there if all the CPUs need it. And it says gained 2 4 bytes holes in on 64-bit arches. And we add a placeholder for TCP TSQ flags next to the SKWMM alloc to speed up TCP W-free in the following patch. We have not added, how many underscores is this? 1, 2, 3, 4? Quadruple underscore cache line align in SMP. This might be done later. I prefer doing this once iNet and TCP UDP sockets reorg is also done. Tested with both TCP and UDP. UDP receiver performance under flood increased by around 20%. That's pretty significant. Certainly at Google scale, that's like huge. Accessing SK filter and SKW key, blah, blah, blah. No longer stalls because SK drops has moved away from a critical cache line, now mostly read and shared. All right. So that's super interesting. I don't know much about caches. sometimes, there are people at places like Google where like, you commit a small commit, or it looks relatively small, and then it has a huge, when you translate it into like dollar value for over the fleet of all of the machines over like a year or whatever, then it can have a small thing can have a relatively high dollar value if it improves cache performance a lot, especially something as omnipresent and low level as UDP performance. All right, so Racksniff says if CPU writes to a cache line, then it has to tell the other. Right, okay, so that's slow, but for reading it doesn't have to tell the other CPU. Okay, yeah, that makes sense. So if you write to a cache line, then you got to notify all the other CPUs. And you're saying that's slow, so I guess that means that you have to wait for some sort of ACK. Or somehow there's maybe some sort of waiting that's required for that. And a program can't control the cache line. A program can't control that a cache line does not go into just the L3 cache. The CPU copies the used cache line into the nearest cache again. Yeah. Okay. I think that's consistent with my mental model. I'm not sure if it's consistent with what I said, that you can't control where things go. But I think what I was trying to say is like if the goal is to make it better to be higher performance to be read only, I think I was assuming that meant that it was in the higher level cache, or L3. I don't know if you want to call that higher or lower level, but it sounds like that doesn't have to be the case, that you get better performance for read-only stuff just simply based on the fact that you don't have to like send a message to all the other CPUs when you do read-only, if I'm understanding the comment correctly on the chat. And by the way, I have to figure out how to preserve the chat when I upload the videos. I haven't figured that out yet, but it's a work in progress. I think that, okay, I'll leave it at that. Okay, so I think that I feel satisfied with what's going on in sock.h. I'll look at the bottom. I'll see if, okay, so I'll turn off blame on GitHub. Okay, sk_wake async, sk_clearbit. I'm just kind of flipping through to see if anything looks unusual or different from what we've seen. It looks like mostly more of the same. Queue receive the datagram if it will fit. Stream and sequence protocols can't normally use this as they need to fit buffers in and play with them. All right, skb prepare for GRO. I don't know what GRO is. Maybe it's an abbreviation of grow. Maybe it needs to grow somehow. Recover an error report and clear atomically. That's sock error. Okay. skstream moderate send buff. All right, something about padding. Unless net driver perform copy break. I don't know what net driver is, but maybe a network driver for a card. Okay, page fragment, sk page fragment. So sk page fragment returns an appropriate page fragment. Use the per task page frag instead of the per socket one for optimization when we know that we're in process context and own everything that's associated with current. And page frag refill. Alas, with timeout socket operations are not restartable. Compare this to poll. Okay. So yeah. Some timestamp stuff. Yeah. All right. Here's a default TCP small queue budget is around 1 millisecond of data. 1 second is much bigger than 10. 10 milliseconds, I guess. Is that what it means? Some Wi-Fi drivers need to tweak it to get more chunks. They can use this helper from their NDO start transmit. SK pacing shift update. It's going to take a sock and an int val. And what it doesn't say is what the, it doesn't say like that the val is milliseconds, but I think that's what this comment is implying. In some code bases, like if you would have the variable named, so like val in milliseconds or something like that. I think that's what val is supposed to be, is you're updating the pacing shift, presumably some sort of time, or however it's parameterized in some way by an int. I don't know exactly what the int does, but yeah, okay. Here's sk dev equiv L3 scope. Oh, that's right shift. Oh, you're saying that this is right shift. Okay, so 1 second, right shift 10. Not much bigger. Okay. In math, this is also the much bigger, not operator, but notation. So I guess it's saying to convert to milliseconds, right shift by 10. Is that right? Okay. Small queue budget is around 1 millisecond. Okay. Well, I'm not sure what it's trying to say, but it's something about the units, right? We've got milliseconds and seconds, and the small queue budget is around 1 millisecond. So this is like the order of magnitude is milli. All right. Yeah. So 1 second is equal to 2 to the negative 10. Okay. All right. So what is 2 to the 10? 2 to the 10 is like 64 or 32. Let's look up powers of 2. 2, 4, let's see. 0, 1, 2, 3, 4, 5, 6, 7, 8. Oh, no, I was way off. 1024. Okay. So 2 to the 10 is 1024. So if we're shifting over 1, I guess we get 1024, right? And then that's roughly 1,000 milliseconds. Is that the idea? So, okay. But we're not shift. So 10 to the 24 seconds is a long time, right? Seconds in hours. It's about 0.3 hours. About 17 minutes. So I'm not sure. So if you take a second and you right shift at 10, unless I'm confusing right and left shift again. Do I have Python? Let me just do this. I got called out for confusing right and left shift. So let's, wait. Am I confusing it again? Okay, wait. So in Python, at least, one left shift 10 is 1024. So I think what you originally said was it was 1 to the negative 10, which is okay, which is right. 1 second to the negative 10. Oh, okay. So it's telling you that it's defining a millisecond as being 1 to the negative 10 seconds. Is that the claim? Which is not quite true in binary, because we've got this. It's true in the metric system, in the decimal system. Okay, but maybe that's right. Okay. All right, so here, if a socket is bound to a device, check that the given device index is either the same or that the socket is bound to an L3 master device and the given device index is also enslaved to the L3 master. So dev equal L3 scope. L3 presumably the network level 3 as opposed to the L3 cache level, which we've just been talking about. So if a socket is bound to a device, check that the given device index is either the same as that or the socket is bound to an L3 master device. Okay. Yeah, okay, cool. Oh, I see. They're saying, recvmsg is saying, I see. So the discrepancy between a second shifted over, right shifted by 10 is only around a millisecond, because of the 10 to the 24 versus 1000 thing. Yeah. Yeah. Okay. I think that's probably the right way to read this comment. Thank you for thanks for working with me on that. Yeah. Cool. Thanks, man. All right. So if a socket is bound to, we just read that. And then we've got a bunch of stuff like sock.def readable, set reuse address, sock bind address, readable. Okay. All right. Let's see. And so now where are we? I have these searches. I'm going to get rid of the searches. Now we're in socket.c. And wait, was I just looking at the sock.h header? Yeah, that was sock.h. Okay. I think I'm going to not look too closely at the .c files, mostly in the interest of time, but also because I think we're beginning to get a sense of how things are, at least I'm beginning to get a sense of how things are structured, what are the important structs, and how does Linux prefer to operate on them. And in the C files, we're going to see a bunch of implementation details, which often, for something that's complicated, is better done after letting your brain process things and coming back with like a fresh perspective. So we'll look at it. We'll see if anything is jumping out at us, but I'm not going to look too deeply at the implementation. We've got some more structs. Socket files have a set of special operations as well as the generic file ones. These don't appear in the operation structures, but are done directly via the socket call multiplexer. All right, so file operations, socket file ops. This module, no lseek. Okay, compat, IO control, mmap. So memory mapping stuff, read and write iterators. LLSeek is like a seek operation, I think, on file descriptors, which makes sense, file operations. Maybe these are the, okay, hang on, let's read this again. Socket files have a set of special operations as well as generic file ones. These don't appear in the operation structures, but are done directly via the socket call multiplexer. So some of these appear to be file operations that are available on sockets. And this is maybe like a definition. Like if you want to know where LLSeek is in this module, is no LLSeek? Or maybe this module is just the owner. I think this module is just the owner, and maybe LLSeek is just defined to be this thing or something. Okay. We've got the PF family names, which we looked at before, but now these are going to be, you can, I guess, take the C, like variable name, the C symbol, and get a string back of the corresponding thing. We've got define spinlock, protocol list. Each protocol is registered here, and then under it is the spinlock. Maybe that is supposed to be up here. Maybe the comment is supposed to be up here. All right, so define spinlock, net family lock. So this is, I guess, net family lock is a kind of spinlock. Net proto family, blah, 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 net families, read mostly. So here's a read mostly annotation. since we talked about read mostly stuff in caches. And then we have support routines, move socket addresses back and forth across the kernel user divide, and look after the messy bits. Support routines. All right, so move socket addresses back and forth across the kernel user divide, and look after the messy bits. I'm not sure what the messy bits are going to be, but this seems to be the thing that's passed frequently for addresses, for socket addresses between kernel and user space. And I don't know what optimization is supposed to look like if you're for something like that. Move address to kernel. I'm just going to check the length and do some optimizations. Otherwise, call copy from user on essentially just the stuff that's passed in. And then we're going to audit the socket address. I kind of want to know what audit is. Whoops. What? Audit socket address. Record audit data for sysbind, sysconnect, and syssend2. All right, but where does it? I guess you can ask it at some point to print out the audit data. So it's going to audit your stuff. All right. So sock alloc inode. I have Linux Pepes. What does that mean, Ahmed? All right, sock free inode, which presumably is going to free an inode. Yeah, kmem cache free. Okay, init inode cache. All right, so we've got inode stuff, managing memory for inodes, sock fsd name. All right. Sock alloc file, bind a socket to a file. And what does it take? It takes a socket, which it calls sock, but it's not a sock. It's not the sock struct. It's going to take some flags and the D name. What is the D name? The protocol name. But where's it getting the file? We're going to create the file. If we don't have a D name, then we'll do some stuff. Maybe ultimately call it the empty name. And then we're going to allocate file sudo, getting the sock inode from the socket, and check whether it's an error. And then we're going to set the sock file to file. So we've allocated a file and set the file private data to the sock, and then stream open sock inode sock file and return file. So this creates a file. I don't think the file is necessarily on disk, and I don't know where it's available. So you get this pointer, or you get, not a pointer, yeah, a pointer to a file, but I don't know if it's like visible in like, if you don't have this particular handle, I don't know if you could find it somewhere in like the directory structure in Linux, but maybe if someone knows, they can let me know. Okay, so, and we're going to export the symbol. So this is, I guess, something you can call outside of this file, which is expected. You can get a sock from a file, return the socket bound to a file. All right. You can sock file descriptor lookup. You can allocate a socket, allocate a new inode and socket object. The two are bound together and initialized. The socket is then returned. If we are out of inodes, null is returned. I don't think I've ever run out of inodes, but it must be, seems like it'd be a real problem. You can release the socket. No inline. Call trace sock send length. I don't know why this should not be inlined, but there you go. Okay, you can sock send message, send a message through the socket, which takes a socket and a message header. And then it calls sock send message no sec. No security, I guess. So first we're going to try to send it with security. All right, passing through LSM. I don't know LSM, but we'll look up Linux security module. Okay, yeah. It's a framework allowing Linux kernel to support without bias a variety of computer security models. Okay, I think we did look this up before. So this is things like AppArmor, SE Linux, Mac, I remember, and whatever Timeo is. Style as Timeo is a Linux kernel security module which implements mandatory access control. All right. Very cool. So this is stuff like error queues. This is the implementations. And maybe the thing to look at is like all of this is, all of this logic is super easy, right? So if you look at kernel send message locked, it doesn't do much, and everything it does, now that we kind of understand what the abbreviations are, everything it does makes sense. And so I think this is a little bit like the hard work is done, defining the API, and now in the language of the API, the behavior is expected. It's unsurprising, which is good. Here's a big if statement. I was going to say it's a switch statement, but it's a bunch of if-else's nested. And so this is sock receive timestamp. And we're going to do things like check whether we need software timestamp, sock receive timestamp tamp ns. I'm not sure how to pronounce this abbreviation, but it's something about getting a timestamp. And this is somewhat surprisingly long logic. We can receive Wi-Fi status. All right, what is Wi-Fi status? So we're going to take a message header in a sock, which is now not a socket, but a sock, and a socket, an SK buffer. We're going to define ACK as an int. We check the sock flag sock Wi-Fi status, and if it's not set, we're going to return, having done nothing. And if the Wi-Fi ACK is, I guess, invalid, then we're just going to return having done nothing. Otherwise, we're going to set ACK to skb Wi-Fi ACK and put C message with message SOL socket, which is not passed in, SCM Wi-Fi status, and size of ACK, and I guess the data, the stuff in ACK. Okay. Sock receive mark, receive drops. All right. Kernel receive message, receive a message from a socket in kernel space. Return value is the total number of bytes received. All right, and this just calls out the sock receive message and sets message control as user to false, and does some stuff with the IOV iterator. IOV iter kvec, which I guess is different from IOV iter vec because it has a K, presumably for kernel space. You can send a page. Yeah, this is fun. If you want to know all about sockets, then socket.c is the place to be. And now that we've looked at the header files a little bit, I think all of this is relatively straightforward for the most part. So let's look at socket. This is socket.c. So let's look at sock.c, and that'll be the last thing I look at today. Lots of Alan Cox, many fixes. There's a chance Alan Cox is the only one who really understands this file. All right. Okay. Some lock stuff. A big table of the AFs, which I forget exactly what it stands for, but we've seen it many times. Basically, the I think the domain is what it's called in the socket API. Address family is what it is. Yeah. Okay. Lock stuff. Some malloc stuff. Memalloc. It might be virtual proc file. Yeah. That was my thought. It might show up somewhere in the proc stuff. It didn't seem to get a name, so I don't know. It didn't seem to like generate a UID or anything like that. So it might. So Nextnerf is saying that like a few minutes ago, I was saying that I didn't know if the what did we do? We like created a file based on a socket, and I was saying I didn't know if that shows up in the file system. And Nextnerf is, I think, assuming that that was the topic when you messaged me, that if it does show up, it's probably in some like maybe the /proc file system. I just don't know enough about the implementation details for sure. And I didn't, I was looking at it kind of expecting that I might do that, but I didn't see where, where it was determined that, where in the proc file system it would go or things like that. So I don't know. It may be there. It may be that you can create one and not have it appear there. And to have it appear there, you have to do something else. I don't really know. Timestamp in nanoseconds. I'm not sure what I was looking at, but okay, but the timestamp in nanoseconds makes sense. Oh, maybe I was trying to look at an abbreviation, I think. Okay. All right. Okay, so more memalloc, which is presumably going to alloc memory. Sock memalloc is allowed to ignore rmem limits to ensure forward progress of swapping. Sock memalloc may be cleared while it has rmem allocations due to the last swap file being deactivated, but there's a risk that the socket is unusable due to exceeding the rmem limits. Reclaim the reserves and obey rmem limits again. Okay, so that's interesting. So sock memalloc can ignore the rmem limits. Presumably some limit on memory that can be allocated. And the reason for this is to ensure forward progress of swapping. So I guess if you're swapping and you're out of memory, you don't want to be deadlocked, I guess. And so allowing socks to have more memory than the rmem limits, I guess, prevents that some sort of deadlocking or something similar to deadlocking, and allows you to make forward progress. I think that's how I'll read that. Let's see. SK error report. Socket timeout. Sock set timeout needs netstamp. Was that netstamp or timestamp? Needs netstamp. And if you are in unspecified or Unix, which is I think the same as local, we're going to say you don't need a netstamp. Otherwise you do. And so it makes sense that you don't need a netstamp if you're not going over the network, but I'm kind of wondering why we don't have a case for whatever the, so there's AF Unix and I think also AF local, and they are the same integer underlying the constant, but it seems like there should still be a case for it. Unless we're concerned that the compiler wouldn't optimize that and they would just call another instruction that didn't matter to execute. I don't know. At any rate, it's not there. All right, sock queue receive skb. Yeah, okay, cool. All right, sock bind index. Let's just scroll through super fast now. Here's a big switch statement. What are we doing? Or maybe it's an if. Yeah, okay, switch on op name. What is this function? Get sk set sock opt. So we're going to set socket options. This is meant for all protocols to use and covers goings on at the socket level. Everything here is generic. Okay, so we can set things like debug, reuse address, and it's just going to peek into the SK and set it. What is valable? Valable is probably passed in, right? Or computed? All right, so valable is whether the value so the value is 1 or 0. What is the value? So val is declared here. And where is it? What? Set socket options, val. I want, we're on line 1020. There we go. That's what I wanted. Okay. So we're going to pass in size of val. Oh, copy from socket pointer into val, I guess. The opt val, which is the thing that's passed in. So I guess we're essentially converting a sock pointer t to a Boolean, or to an int, which we're going to consider to be a Boolean. All right. I don't know why I don't know why the kernel seems to use ints for booleans. Maybe it's about, I don't know if there's variation around the size of booleans, and that int is more, there's some reason to prefer int in something low level. I don't know. I don't know why it can't just be a bool. At any rate, we're going to set the socket options. We're going to look inside of stuff and like set a flag, and that's straightforward. There's some logic for like things like so send buffer. Don't error on this. BSD doesn't, and if you think about it, this is right. Otherwise, apps have to play guess the biggest size games. Receive buffer and send buffer are treated in BSD as hints. Okay. So val is going to be the min, I guess, of val and read once system control wmem max. And ensure val times 2 fits into an int to prevent max t from treating it as a negative value. Okay, we don't want to overflow whatever val is val times 2. So val is equal to min. I guess min t is going to take a type. Maybe? Is that what this is? Of the val and int max over 2. And I guess this is some sort of locking operation. And we'll write once the thing that was passed in, but with some min operations. So you may not get everything you asked for. It's considered a hint. Is that what it says? Somewhere it says hint. Or treated as hints. So you don't have to play guess the biggest size, by which I'm guessing it means that it's not the caller's job to figure out what's going to fit in memory or whatever. And so this logic does that for you. All right, well, let's look at keep alive. Oh, this is just setting an option, so that's not so interesting. All right, I think I'm basically done. Here's my scroller here. We've got some CMessage stuff. CMessage send. We're going to switch on CMessage type, whether it's mark, timestamping old, transmission time, rights and credentials. Anything else? Some page stuff. This is interesting. Static branch unlikely. I kind of feel like I want to know what this is. The static branch unlikely branch will be generated into the code with as little impact to the likely code path as possible. Currently, trace points are implemented using a conditional branch. The conditional check requires checking a global variable for each trace point. It's a deprecated API? Wait, is this part deprecated? The updated, okay. Static key false is replaced with static branch unlikely, I guess. Static keys allows the inclusion of seldom used features in performance-sensitive fast path kernel code via a GCC feature and a code patching technique. An example is if branch unlikely with key do unlikely code else do likely code. The static branch unlikely branch will be generated into the code with as little impact to the likely code path as possible. And something about trace points. As we increase the number of trace points in the kernel, this overhead may become more of an issue. In addition, trace points are often dormant, disabled, and provide no direct kernel functionality. Thus, it is highly desirable to reduce their impact as much as possible. Although trace points are the original motivation for this work, other kernel code paths should be able to make use of the static keys facility. GCC adds a new ASM goto statement that allows branching to a label. Using the ASM goto, we can create branches that are either taken or not taken by default, without the need to check memory. Then at runtime, we can patch the branch site to change the branch direction. For example, if we have a simple branch that's disabled by default, like this one, by default, the print K will not be emitted, and the code generated will consist of a single atomic no-op instruction in the straight line code path. When the branch is flipped, we will patch the no-op in the straight line code path with a jump instruction to the out-of-line true branch. Thus, changing the branch direction is expensive, but branch selection is basically free. That is, a basic trade-off of this optimization. All right, so I'm not following exactly what's going on at the like assembly code level, but this is an optimization where you can tell the compiler which things are likely to happen, and somehow there's this like patching thing. I don't know how you decide that you're actually going to execute the unlikely branch, but if somehow you detect that you are in the unlikely branch, you have to like exert more effort to get there. But the benefit of that is that for the happy path, for the most likely thing to happen, you're exerting slightly less effort, and you're doing that many times over. And that, I think, is the idea of what the optimization is. Okay. All right, so page refill, release sock. All right. skmem raise. Wait, I'm getting some comment to look at 1147. Is this related to the... .47. Yeah, this is... yeah, I think that's what I was saying, right? Oh, maybe you were commenting on... I was saying min t... so the min function, like the mathematical function, takes 2 arguments. And I think maybe you might be responding to me saying that min t takes a type as the first argument. This is definitely a min, but it's got this first argument, and I'm not sure exactly what it does, but I'm going to guess that like it somehow configures min t to use the right logic for computing the minimum. All right. Okay. I think that's basically it for sockets for now. We will continue doing Network Wednesday, so this is not going to be the end of seeing what's going on with sockets or socket-related things, and we'll probably come back to the kernel a fair amount, because one of the things I would like to do in this show is have an appreciation for how all of the things work. So we're going to do some things at cloud scale, which is like, kind of thinking about addressing a cluster of computers, which might be spread out over large geographic areas, thinking about that as like a single computer. But we're also going to be looking at stuff closer to the hardware. And so that's what doing some of this kind of kernel-y stuff is about. And that's all for me. I'll have my schedule for next week up probably today. So keep an eye out for that. And thanks much for watching. And thanks for the folks who were able to watch live, and for chatting with me, and for chiming in when when I'm not sure what's going on. I really appreciate that. I'm enjoying this a lot. So thanks, and have a good day. Bye.